Hello everyone, and welcome to today's webinar. See which proteins like it hot with new isothermal applications on UNCLE. I am Kaylee Bach of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Unchained Labs. To learn more, visit unchainedlabs.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. I'd like to now welcome our speaker, Andre Mueller, PhD, Product Manager, UNCLE at Unchained Labs. Dr. Mueller, you may now begin your presentation.
Thank you very much for this introduction, and thank you all for joining me this morning for my presentation that I titled, See Which Proteins Like It Hot with the New Isothermal Applications in UNCLE. When you're working with proteins and you want to test proteins for their stability, you usually run a thermal ramp. Thermal ramps are quick, about 2 hours, give you a lot of information about the melting and the aggregation behavior of the protein, and allow you to narrow the list of candidates down so you have fewer candidates to focus your subsequent work on. However, long-term exposure is also something you want to keep in mind, because I'm sure you've all been there. I certainly have. Living in the Bay Area with the proverbial fog, you walk out in the morning, oh, it's not going to be sunny today. I'm not going to get burned. I don't need sunscreen. And then in the evening, everything is red. Long-term exposure is something to work with, something to think about, something to be aware of. And sunscreen helps. And in the same vein, looking at the isothermal stability of a protein can help you prevent bad surprises later on in the development process. When we are talking about isothermal stability of proteins, what we want to look at really is we keep our proteins at a steady temperature over a long period of time, and we monitor their behavior, their unfolding behavior, and their aggregation behavior. And that's things that you can do with the new isothermal applications in UNCLE. Why is this important? Well, you know, what people oftentimes do in developing a protein candidate further is they do a thermal ramp first to narrow down the number of candidates, and then they do the isothermal testing at the very end of the development process. That's because isothermal, as it is oftentimes done, is pretty cumbersome. You have to have a large amount of protein solution. You have to store it. You have to run it, for example, in HPLC to look at aggregation and loss due to aggregation. And all these things make isothermal testing, make long-term storage testing kind of cumbersome. Even accelerated stability testing is not really that super fast. It still takes a considerable amount of time and also of volume. When using the new isothermal applications in UNCLE, we open a door to testing both thermal ramping behavior and isothermal long-term behavior at the same stage of the candidate selection process, so early on. It is so easy to run isothermal in UNCLE. You can run between 1 and 48 samples at a time so that you can use both thermal ramping experiments and isothermal long-term storage experiments to narrow down your list of candidates. And I think that's really the power of it, that you get access to this very important metric of your protein early on. And what I will talk about in this presentation, I'll give you two case studies where we looked at two proteins and compare results we have from thermal ramps with results we have from longer-term isothermal exposures. Before talking about that, let me first briefly review what we mean when we talk about protein stability. Proteins, of course, we all know they have a native structure, they have a native fold, and that's in an equilibrium with the unfolded state. So by increasing the temperature, you can push this equilibrium towards the unfolded state. This is what we refer to as conformational stability of a protein. To make things more complicated, proteins also do other things. They can also aggregate, something that we call the colloidal stability. And both the native state can aggregate and the unfolded state can aggregate. So in order to monitor the behavior of protein, to monitor protein behavior, protein stability over time or over temperature, we want to keep both the conformational and the colloidal stability in mind. We want to keep an eye on both of these. And the right tool for the job to do this is UNCLE. UNCLE combines 3 different measurement modalities in one instrument. So we can measure fluorescence, we can measure static light scattering, and we can measure dynamic light scattering in a temperature-controlled environment. In terms of the fluorescence, we use 2 different laser systems to excite fluorescence. We use a UV laser of 266 nanometers, and we use a blue laser of 473. That way we can excite both the protein intrinsic fluorescence with the UV laser and potential dyes that you want to use. That's what the blue laser is for. At the same time as exciting with two laser systems, we monitor the full spectrum of fluorescence emission of the analyte. So we are very flexible in looking at the protein in the shorter wavelengths or reporter dyes like Cipro Orange in the longer wavelengths. In the two case studies I'll show later, we'll cover both of these topics as well. The signals or the light that is scattered from those two lasers is what we use in our SLS experiment. Static light scattering is a readout of molar mass. As a protein aggregates, the molar mass increases. So the SLS signal is something we can use to assess protein aggregation over time or over a temperature gradient. We have that SLS data for both of our lasers, so both the UV laser and the blue laser. That gives us a very high sensitivity of detection of aggregation, and at the same time gives us a big dynamic range so we can cover orders of magnitude of aggregation occurring. UNCLE also packs dynamic light scattering. It sounds almost like static light scattering, but is fundamentally different. Here in this case, we look at the diffusive behavior of our analyte, and that is an orthogonal measure of aggregation that you can apply. Temperature control, UNCLE can be set in temperature between 15 degrees Celsius and 95 degrees, and we can do that for a ramp, but we can also, of course, do this for isothermal experiments and keep the temperature steady over longer periods of time. The heart of UNCLE, the sample introduction into UNCLE, happens in the unis. The unis are arrays of 16 quartz cuvettes in an anodized aluminum frame. That anodized aluminum is there to make sure that the temperature conductance is high, so the temperature of the sample is what you've actually set. And these cuvettes have a volume of 9 microliters. They're open on both ends, really easy to load. Capillary force sucks the sample right in. And then these unis are clamped in the blue uni frame with silicone seals. So these silicone seals are consumables, and they seal off the quartz cuvette, and you don't have to worry about evaporation. The 9 microliters of your sample are safely sealed in the uni, and then you can use that as in your temperature ramp or also in your isothermal experiment. When you run a protein in a thermal ramp, so in this case here, you see individual spectra building up. We have one spectrum recorded for every degree in our temperature ramp from 15 to 95, so 80 spectra here in this case. And what we're seeing as this temperature increases is that the protein unfolds. And you see that the fluorescence spectrum changes. The maximum, first of all, gets lower, and it shifts to the right. It shifts to longer wavelengths for this protein. That is because the aromatic amino acid residues that are responsible for the autofluorescence of the protein, the phenylalanines, tyrosines, tryptophans, are usually buried on the inside of the protein in a hydrophobic environment, and they show fluorescence. As the protein melts and they are turned outside to the hydrophilic environment that the protein is in, their fluorescence behavior changes. And when we monitor the fluorescence in the temperature gradient, we can assess unfolding that way. This shows also the full spectrum of fluorescence of UNCLE. So we record from 250 to 720 nanometers. I cut this off a little bit here because it's just the baseline, but you can look at the protein intrinsic fluorescence here in the blue section. If you had a dye in here, you would see that over here, and I have an example for that coming up later. This is the raw data that UNCLE delivers, so the spectra, and then we process that data to a graph that looks something like this. We have our fluorescence here on the left y-axis. The x-axis is the temperature. This is a temperature ramp experiment. And we have our static light scattering in green on our right y-axis here in this case. What we're showing for fluorescence is what we call the BCM, the barycentric mean. That is the spectral center of gravity of our fluorescence emission. It is the wavelength that separates the area under the curve into equal halves. With this kind of analysis, we integrate over the entire peak of the fluorescence emission, so about 130 wavelengths, which gives us a really high signal to noise ratio and a calm signal. So if we follow this, we can see how as the fluorescence emission maximum shifts in wavelengths, we see that represented here in the curve. And then there are two inflection points in this curve, which the software determines by looking at the differential. Those would be the two melting curves, the two melting points, sorry, Tm1 and Tm2 of our analyte. That is what we want to find out in our temperature ramp. At the same time as looking at the unfolding behavior, we also get a glance on the colloidal stability, because the static light scattering signal is rather boring, it's rather flat, and that at around 80 degrees that starts spiking, because that's when the sample starts aggregating. This aggregation for this specific sample here happens in concert with the Tm2, with the second melting event. So much the introduction, so much as to the theory of what we find out in a temperature ramp. Let's take a look at the first case study. In this case, we have a monoclonal antibody, commercially available monoclonal antibody in three different formulations. We have the no salt condition in green. We have low salt, 50 millimolar sodium chloride in blue, and we have high salt, 250 millimolar sodium chloride in yellow. Otherwise, the buffer that the system is a 25 millimolar histidine buffer of pH 7.4. So when we look at these three formulations that are varying only in their salt content, we look at the melting behavior, these three formulations show pretty much comparable, similar melting behavior. So it's varying, melting points vary between 69.5 and 70.4 degrees Celsius, so about 1 degree difference. The high salt condition in yellow seems to be slightly less stable than the no salt and the low salt condition. When we look at the aggregation behavior, and I forgot to mention this earlier, but we measure these two parameters at the same time in the same volume. So the sample is in the uni, and we record static light scattering and fluorescence concomitantly, same time, same sample, same temperature point in this gradient. Looking at the aggregation behavior, we can see that the low salt in blue, let me put the arrows in for the actual aggregation points. So the low salt condition, 50 millimolar salt, starts aggregating first, and the no salt and high salt conditions, they start aggregating a little bit later. These two aggregation points are about 1 degree different. This one is 66 degrees, so this is about 7 degrees lower. So there's significant destabilization in terms of aggregation of our sample in the low salt condition. But differentiating between the no salt and the high salt is going to be difficult. That's what we can learn from the temperature gradient. As I was mentioning earlier, we also measure DLS. So let's take a look at what that shows. And our DLS experiment actually confirms that the sample aggregates in our thermal ramp. When we look at the DLS spectra that were recorded, or the DLS signal, I should say, it's not a spectrum, at 15 degrees, we see that the monoclonal antibody shows a typical diameter of about 10, 11 nanometers. And then as we have ramped the temperature up to 95, you can see that these diameters have increased to more than a micrometer. So DLS confirms that our sample has aggregated and confirms what we saw from the static light scattering signal. Now, what can we learn about our monoclonal antibody in an isothermal experiment? So in this case, we have our monoclonal antibody, we incubate it at a given temperature over long periods of time, and we see how our fluorescence and our static light scattering signal will change. We can also look at the dynamic light scattering signal, of course. Example data, so this is not quite a case study yet, I'll get to that in a second, but let's look at some example data here. We also see that if we look at the fluorescence in blue on the left y-axis, that the BCM value shifts, and this is an isothermal experiment over 24 hours at 58 degrees. And at the same time as the fluorescence signal is monitored and changes, we also monitor the, same time as the fluorescence signal is monitored and changes, the static light scattering signal is also monitored and changes, indicating that the sample is aggregating. So again, in UNCLE, we measure fluorescence and static light scattering at the same time and can deduce what our sample does in this isothermal experiment. This experiment was run at 58 degrees Celsius. And I think one of the most important questions when running an isothermal experiment is, how do you want to design it? How do you choose which temperature you incubate in? Some people like using melting temperature -5 degrees. Other people use 42 degrees, 47, 60 degrees, because they have an incubator set at that temperature. It's really quite flexible, and there is not really any consensus on how you would want to do it. So for our experiment, what we did is we looked at our melting and aggregation temperatures and then chose 60 degrees as a temperature for our isothermal. That's about 10 degrees lower than the melting temperatures, and it's about 6 to 8 degrees lower than what we saw for aggregation. What I think is really one of the strengths in UNCLE is that these isothermal experiments are so easy. So you could actually run several of them, one day at 60 degrees, next day at 65, next day at 55, and really find out what the ideal temperature for your isothermal, longer term isothermal is. So you do like a scouting experiment. In our case, we chose 60 degrees and we actually did see something. So let me show what we found. So looking at the static light scattering intensity from a monoclonal antibody, and this is one at 266, so using the UV laser, we see that the low salt condition in blue here, 50 millimolar salt, starts aggregating first, and the high salt condition and the no salt condition start aggregating later. So until about 3 hours, they behave similarly, and then we really see a difference between the two conditions. So by running a 6-hour isothermal experiment at 60 degrees, we can really show that although the aggregation temperatures between yellow and green, between high salt and no salt, are only different by 1 degree Celsius, the aggregation behavior in the isothermal experiment over 6 hours really shows us which is the most stable formulation is. As I was mentioning, we are not only measuring the static light scattering at 266 nanometers, we're also measuring at 473 nanometers, and that result confirms what we saw for the short wavelengths. Also here, the aggregation of the low salt condition, 50 millimolar salt in blue, is occurring first, and the most stable one is the no salt condition here in green. The new isothermal applications in UNCLE also allow you to determine rate constants. I'm showing this down here. So for the blue condition, the low salt condition that shows the highest aggregation, the K1, the rate constant, is the lowest value. So we also, in addition to looking at the graphs by eye, we also have a mathematical metric for the aggregation in the form of the rate constants. Isothermal experiments like this can take a lot of time. So in this case, it only took 6 hours, but you can in principle devise an isothermal that takes several days, takes up to a week, and that kind of sort of locks in your instrument for the duration of that experiment. But because isothermal testing takes time, and because we know that our samples are safely sealed in the uni, we thought it might be really nice to have another set of applications in UNCLE that we termed the out-of-the-box apps. As the name suggests, you incubate outside of UNCLE. You take your sample, read the signal, dynamic light scattering, static light scattering, fluorescence. You take the uni out, put it in an external incubator, incubate it there as long as you like, put it back into UNCLE and add another data point. So the file, the results file, is not locked. You can add, you can append data points and evaluate, analyze that data together, and when you have all the data points in that you would like to have. And also, you're not tied in terms of the temperature, the timestamps. You can choose how many hours you want in between the individual reads. What does this look like in practice? So here is an example of our monoclonal antibody. We measured static light scattering at 473 nanometers, so aggregation behavior at time point 0, at 20 hours, 40 hours, 60 hours. And again, we can clearly see that the low salt condition in blue 50 millimolar salt shows aggregation that starts sometime after the 20-hour time point. And we can grab that, we can measure that with our out-of-the-box experiment. For the 20 hours between those reads, UNCLE is free for other things. So you can start an out-of-the-box experiment for isothermal, take your sample out, put it in an incubator, and then use UNCLE for the time being for other experiments like a KD run, a B22 measurement, or a thermal ramp for other researchers or other projects. So it gives you a lot of flexibility in how you use your instrument. We can do this OTB out-of-the-box experiment not only for static light scattering, we can also do this for dynamic light scattering. So here included DLS in this daily snapshot, time point 0, time point 20 hours, time point 40 hours. And we have one light blue sample here kept at 4 degrees, and you can see the 12 nanometer diameter of that IgG remains constant in the fridge, but at 60 degrees we see clear increase. So this out-of-the-box experiment gives you a good way of following the aggregation of your sample. For our A monoclonal antibody, here's a summary. All the aggregation metrics agree. So if we look at the aggregation from temperature ramp versus the ones from the isothermal experiments and the OTB out of the box, we can see that the low salt condition really is the worst in terms of aggregation. And if you had to choose one, it's probably a 25 millimolar histidine at pH 7.4 without salt is going to be the best one that you can look at. That concludes the first case study. Let's take a second case study into account here, and that used RNase A. RNase A is a small protein, about 17 kilodaltons, and it's very low in aromatic residues. So if we look at the fluorescence, here is the monoclonal antibody we just had with the fluorescence after 266 nanometer excitation, and here's the RNase A. You see it's a much lower fluorescent yield, and if you looked at the BCM curve for RNase A, it'd be pretty flat. It doesn't show much change because there is just very few aromatic residues in here that would be usable in intrinsic protein fluorescence. What you do in this case? Well, we can use a reporter dye. So we used Cipro-Orange in this case. Cipro-Orange is a dye that interacts with hydrophobic protein patches. So as the protein unfolds, these hydrophobic patches are presented. Cipro interacts with those and increases its fluorescence. So as you see that here on the right side, if my pointer moves with me, we have the folded protein where Cipro-Orange has nothing to interact with, so there's very low fluorescence yield. But as the protein unfolds, or is unfolded, I should say, we see a much higher fluorescence yield from the Cipro interacting with the hydrophobic patches of the protein. So when we look at thermal ramp experiment using RNase A and Cipro-Orange, this is what we see with our three formulations, the same formulations as before. We see no difference in the melting behavior between those three formulations, and we also don't see any aggregation happening. So in terms of RNase A, there's really no way we can judge which of these formulations is better and which one is the one we want to use for further optimization studies. So what we did is we also took this analyte here in an isothermal experiment. And what we actually see here is we see aggregation that starts around after 10, 11 hours. In the no salt condition in green and in the low salt in blue, we can see clear aggregation occurring. This is looking at the 266 nanometer light scattering intensity, whereas in high salt, it remains flat. So no aggregation in high salt, aggregation in no salt and in low salt. So in this case, we need the isothermal experiment to really be able to differentiate between the different formulations. We also, of course, wanted to try the new out-of-the-box app for this analyte. So this is the static light scattering. We look at the Z average diameter over 3 days, measured once a day. And you can see that in high salt, confirms what we saw from static light scattering. In high salt, it remains flat, whereas in low salt and no salt, here in green and blue, we see significant aggregation that is already visible almost after the first day. Again, in OTB experiments, out-of-the-box experiments, you are flexible in staggering your data points whatever way you want. The files themselves are time-stamped, so the instrument or the software will keep track of the time elapsed. But for these 24 hours between those reads, you can use your instrument for other purposes. So summarizing the second case study of RNase A, only the isothermal experiment is able to rank the different conditions. The ramp doesn't give us any difference. It looks good in all cases, but looking at it isothermally, we can really differentiate between the formulations and see that only the 250 millimolar salt condition is really good and something that we want to look into for further refinement of our formulation. So to summarize this, UNCLE, the first all-in-one stability platform, has a set of tailor-made isothermal stability tools, both the regular isothermal tools and the out-of-the-box tools that allow you to start using long-term stability testing early on in your candidate selection process. We, of course, retain what we had before, the Tm and Tagg applications. We can still run DSF applications. We can also take a look at viral capsid stability. And we also actually have an isothermal application that is specifically coined towards viral vectors. Not the topic of this webinar, but we'll talk about this in the future. You can also still use UNCLE's DLS for a DLS with polydispersity analysis, or combine it with a thermal ramp. You can look at colloidal stability parameters like KD, B22, the second viral coefficient, or G22. You can use UNCLE to look at thermal recovery, viscosity, and also at isothermal chemical denaturation experiments. So in with all this, Uncle is really your lifeguard at the beach. It'll watch over your 48 samples for 2 hours. It'll also look over them for a day or 2 days and tell you when it's time to put on sunscreen. Uncle is your all-in-one protein stability platform. Makes sure that all of your analytes behave the way, or you know how your analytes will behave. And with that, I'm going to be happy to answer any questions that have come on. Thank you very much.
Thank you, Dr. Mueller, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen, and we'll answer as many of your questions as we have time for. All right, so let's get started. Our first question asks, does Uncle have tools for 21 CFR PT11 compliance?
Thank you very much for this question. Yes, Uncle does have tools for 21 CFR Part 11 compliance. We have an add-on to the software that adds an audit trail, and we can also qualify the instrument. So Uncle is ready for 21 CFR Part 11 compliance, absolutely.
Wonderful, thank you. Next question here. How flexible are the new isothermal apps in Uncle?
Thanks for that one. I think they are flexible on many levels. First of all, there is a whole host of different ones. We have 3 isothermal applications. Isothermal, the most flexible one, that allows you to choose whatever excitation wavelengths you want to use and what analysis options. And then we have isothermal for Cipro Orange users. And then we have an isothermal for viral vectors, or for capsid characterization. And then we have the 2 out-of-the-box applications that are, one is open and you can use it for whatever analyte you would like, and then one that is tailored to using to be used with viral vectors. So it's 5 applications, which is in itself flexible. And then, of course, each of them you can use DLS and or SLS as you like. And then when it comes to the data analysis, which is something we will focus on in an upcoming live demo, we have different fit models. So we can analyze both monophasic changes, biphasic and triphasic. So overall, I think we are giving researchers interested in isothermal work a whole toolbox for them to work with. And I would describe it as very flexible.
Wonderful, thank you. Next question here asks, can you use a uni for several tests?
The uni is our sample holder. So it's a 9 microliter quartz cuvette. It's an array of 16 of them. And the individual quartz cuvette is designed for single use. So you can, of course, use 4 of those 16 today and the other 12 tomorrow. But one single cuvette is designed for single use. So imagine you're denaturing a protein in there, and then how would you know if you can wash it all out again? So it would be really hard to keep those clean afterwards. So they're designed for single use. Also, they are sealed with silicone gaskets, and we provide plenty of silicone gaskets with every set of unis. So these are also consumable. So the Uncle consumables are the unis, and you use them once. They are single use, but you can use different ones in the array of 16 at different time points for sure.
Great, thank you. We're getting some great questions in from our audience, so I want to continue to encourage you to drop those questions into that Q&A box there on the left side of your screen. We'll continue with our next question here. Can we use isothermal apps to study AAV and other viral vectors?
Yes, we can. We have the viral vector toolbox in our software that has apps for viral vector stability characterization, both in thermal ramps and also isothermally. So I think I was alluding to it in the talk earlier that this is going to be the topic of an upcoming webinar. And yes, there is a specific isothermal application for viral vectors, and you can monitor the stability of the capsids in and of itself, and you can also monitor the loss of payload, the genome ejection of the viral vector over time.
Great. Next question here asks, when would you use reporter dye?
Thanks for that question. We used in the study with RNase A, we used Cipro orange, the reported dye, because there was very little intrinsic fluorescence of the protein. So that's one condition in which you would want to use Cipro orange. Another is if your lab has been using DSF for a while and you have some legacy protocols that you want to continue using and they just call for a reporter dye. And then I think the third scenario that I can think of right now would be if you had a situation where your buffer is quenching fluorescence of the protein. So if, for example, ATP is in your buffer, or if you have ascorbic acid present, if the buffer conditions quench the intrinsic fluorescence of the protein, then adding a fluorescent dye can help and can make the system measurable. So it adds to the flexibility of the system to be able to use intrinsic fluorescence and or dye fluorescence based on the experimental needs.
Great. Well, it looks like we have time for one more question here, so we'll go ahead and wrap up with this one. Are there any other changes that were introduced in the new software?
Yes, there are. I mean, I've worked for it for a couple of months now, and I really like using the new software. And everybody who has used Uncle software before, I think, will enjoy using version 6. We have, for example, introduced replicate groups. So if you're running an experiment in triplicate, the software is now able to show you the average of the curves of the 3 individual measurements and also show you the standard deviation right in the graphic form. We have also worked on the colors, the color assignment to samples, and make the DLS display a little bit more condensed, a little bit more easy to interpret right away. So overall, I think we have been listening to what our users have been asking us for and implemented a number of changes. So it, of course, version 6 packs the new isothermal applications, but also the overall look and feel of the software has improved a lot. And I think it's great fun to use it. And I encourage you to try it out and see for yourself.
Fantastic. Well, thank you again, Dr. Mueller, for your time today and your important research. We would also like to thank LabRoots and our sponsor, Unchained Labs, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today, and those submitted during the on-demand period, will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand, and LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care, everyone. Goodbye.